All right, everybody. So we are recording. I know I tried to turn this into a non-formal situation by sitting with you guys, but because I'm up here and stuff like that, and I want to draw something up on the board. So, all right. On Friday, we discussed phase changes between our three separate states of matter, right? So we talked about solid, liquids, and gases, and we talked about this, and this, and then we talked about this, and this. Crud, I did that backwards. What? You missed that, say crud. Here, alright, and then here, and here. Alright, so we talked about naming these 6 phase changes, alright? I won't go over all of them right now, because I think most of you could probably know of them, but anyway. What? Like changing something from one state of matter to another state of matter? Yeah. Do you know the names of all of them? Condensation, vaporization, yeah, stuff like that. More importantly, though, for our standpoint, right, some arrows are red and some arrows are blue. Why? Temperature. Let's go more generally speaking. Energy, right? In order for us to go from solid to liquid, what do we have to do? Increase the energy of the particles, right? And go from liquid to solid, then we got to decrease the energy, right? So increase energy, arrows are in red, decrease energy, arrows are in blue, all right? And we talked about, we can figure out how much that energy changes using Q and M and C and delta T and all, and do those calculations that we did for this specific heat level, okay? Good with that. Okay. All right, going back to the book, right? Particles can move from one phase to another, so we talked about that. Sorry, Hunter, this is page 366, because that's what we kind of started on Friday. But we also discussed that while energy is one important factor, right, there's another factor that can affect those phase changes, and that factor is what? Pressure, right? And specifically, that pressure is affecting the attraction of the particles. How tightly are they packed together? And we talked about the idea that on the top of page 368, maybe? Yeah, 368. Here, if we decrease the pressure of an object, or sorry, we decrease the pressure on a substance, the temperature at which those phase changes occur actually decreases. And that we can look at what we call the boiling or the vaporization point of a material depends not only on its temperature but also on pressure. That here, go ahead, huh?
Pressure increases, then does that mean temperature also?
Yes, when we're talking about phase change, like vaporization right here, okay? So because when we talked about kinetic theory, there's really 2 factors that determine what state of matter something exists in: the energy of the particles and then the attractions between them. Pressure can, while not exactly change the structure of a substance, it can cause those particles to be squeezed closer together, and that by nature, or so kind of by default, makes them attract each other more. Does that make sense? All right, so, and this is the idea, we kind of talked about this on Friday, that as we go to higher elevations, like we go to a Denver or Salt Lake City or something like that, when you cook something on the stove, your water is boiling, but the water is not as hot as it is here at lower elevations, because that pressure is decreased, and that makes those particles more easily transfer into that gaseous state, right? So when we talk about like cooking, if you look at like boxes of macaroni and cheese or things like that, you'll see that they're high altitude cooking instructions, because those particles aren't as warm because of the idea that the pressure is decreased. Go ahead.
Isn't that necessarily like the temperature out there at the time? It was like pressure and like vaporization.
This is a combination of on the y-axis what the pressure is, and then the corresponding temperature at which those particles will release from the gaseous phase from the liquid phase into the gaseous phase. Okay, and that temperature decreases as the pressure decreases.
So it would be like freezing cold on that ice, but you can still cook like.
Very much so. Okay. Well, now see, cooking
It'll
it'll
boil
boil, but is it hot?
Isn't boiling
No. Boiling means that something is transferring from a liquid phase into a gas phase. But this chart is showing us that how that occurs not only depends on the temperature on the x-axis, but it also depends on the pressure on the y-axis. All right? Hana, have you ever seen there's things you can get at like Spencer Gifts or like online weird plate, like kind of funny things. They have something called a hand boiler. You ever seen it before? Anybody know what I'm talking about? Kind of looks like a barbell made out of glass. So here, I'll do this for the sake of those not here. Kind of looks like something like this, okay? And then in the bottom here, there's a colored liquid. It's water that just has food coloring in it, okay? But you can grasp it with your hand and it will start boiling. Okay? It just starts boiling right in your hand, okay? Because the pressure inside of the hand boiler is reduced. So when they make it, they seal it off with a low pressure. The boiling point, the pressure is so low that the boiling point of water at that pressure is about 37 degrees Celsius. You know what else is 37 degrees Celsius? You. So the heat from your hand, the energy flowing into it, is enough to give the particles of that liquid enough energy to escape into the gaseous phase, just because there's no pressure holding them together, right? It's also the reason why astronauts need pressure suits, or what we call space suits. As the altitude increases, we see from this chart, right, the pressure decreases. On a mountaintop at 3,000 meters, the boiling point of water is reduced to 90 degrees Celsius. Okay, no problem. But when you get down here, right, the pressure is so low that water starts to boil at 37 degrees Celsius. What's 37 degrees Celsius, Vlad? Humans are 37 degrees Celsius. So if you get high enough elevation, the pressure is so low that just your body heat is enough to boil water. That's a problem for you, because what is your body mostly? Water. So once you get above 63,000 feet, the pressure is so low that the water in your body would start boiling on its own. It's not hot, quote unquote, it's not hot, but because the pressure is so low, your body would start to boil itself. All right? Say again? Maybe. So what starts the space suit, while it is protection and stuff like that, it's actually an artificial atmosphere. That's what it's for. The pressure inside the spacesuit is close to a normal atmospheric pressure, so your blood doesn't start boiling. Because that's not good. If your blood starts boiling, that's generally speaking not good. Right? Good. So you probably didn't get too deep into this in chemistry class. So yeah, discussing So. Those are the things. Those are the things that that could become relevant. So other applications of this, right? Generally speaking, when we're here on Earth, right, the temperature is a bigger change than the pressure. Obviously, elevation makes a change in pressure, but most of us don't experience too much of those elevation changes very quickly, right? Temperature is the easier one for us to do. So when we talk about using these phase changes to help keep us cool, down on page 369, down at the bottom on the right, your body has evolved to use this phase change to help us maintain a constant temperature, or at least a fairly constant temperature, right? So you sweat when it gets warm, right? When you look, right, the picture down at the bottom of page 369 explains how sweating helps you keep cool, right? Here's a droplet of sweat. That droplet of sweat, temperature-wise, where does it come from? Where does sweat come from? Your pores, inside your body. So when you sweat, is that sweat any colder than you are? It's not. It's exactly the same temperature, all right? But we talked about that evaporation occurs when particles around the outside edge gain energy or have enough energy to release the liquid phase. They're not really gaining any energy from your body, because what's the temperature difference between you and the sweat that's surrounding you? There isn't one. Heat flows from hot to cold, but if two things are the same temperature, that doesn't do anything, right? But what does happen is that the particles on the outside edge have enough energy to escape into a gas phase. Just because, remember, temperature is an average energy, not the absolute, or not the energy of every single particle. Some particles have more energy, some particles have less energy. The high speed particles, the high energy particles in that drop of sweat are released because they have enough energy to break the attractive forces of all the other particles holding them together, right? If the higher energy ones are released from the drop of sweat, what happens to the average of your drop of sweat? It decreases. And if the average decreases, that changes the what? The temperature. And now the drop of sweat is a lower temperature than your body. So what happens? Well, what happens first? You transfer energy out of your body into the sweat, right? And that causes more particles to be released. But what did we talk about this? What did we learn about the specific heat of water? It's very high. So how much energy is each drop of sweat gaining from your body? Kind of a lot. That's why it's an efficient way of doing it, right? So that's one of the things that helps us as humans, right, evolutionarily speaking, helps us because we can cool ourselves in this manner, right? If you watch like Animal Planet and stuff like that, okay, so this helps us because it helps us maintain temperature at a level where metabolically speaking we can function, you know. Lots of animals don't have the ability to sweat, right? The most obvious one, because we see it all the time, right? Snakes. It's not what I was thinking. I was thinking dogs, because we see dogs usually a lot more than snakes, right? So, but dogs cool them down. Dogs cool themselves down how? By breathing weirdly. They breathe heavily because they basically sweat out of their tongue. Right? Like that's how they get rid of that heat, right? Other animals like cheetahs, for example. Cheetahs don't sweat. So that's why cheetahs are very, very fast, but they can't maintain that speed for a long time because it involves energy and they have to get rid of that excess energy. So they can have these huge short bursts, but then they can't maintain that speed for a long time because they don't have the ability to cool themselves down and get rid of that extra energy, right? We do, and that allows us to maintain that level of activity, right? We're not fast, but relatively speaking, we can travel for a long distance. So we go back to crossing the savannah or whatever we did when we were evolutionarily developing whatever. So yes, what? Yes. Where? Give me a page. So, here, pressure. Pressure is force over area. Okay, that's how we define pressure. The force that we're talking about, generally speaking, is the force of collisions of particles running into wherever we are. So as you sit there, Fuad, right, like this, particles of the air, particles of the atmosphere are running into your body. Right? They hit, they apply a force, they bounce off. Newton's third law kind of thing, you know. So the pressure is defined as a force unit, N, over an area unit, meters squared. Now, there are lots of other units of pressure that we use, but that's how we sort of define it. It's kind of like, I'm trying to think of it. Does that make sense, or do you want me to explain more? Okay, so yeah, that's how we define pressure, but we have a lot of other pressure units that we use. Things like kilopascals here, what else? Atmospheres is another one. Those are all basically force per area, but we do just different ways of representing the same pressure. Okay? Is that good? Your soul is dead, or? Oh, all right, page 372. Page 372. On page 372, down at the bottom, you will see figure 1023, temperature versus heat added or removed. We refer to this as a heating curve, or it could be a cooling curve, depending on which way we go. This is a heating curve because we're starting low. So you'll see this is for water, ice down at the bottom, right? But then there's this plateau. The y-axis on this graph is temperature. So if there's a plateau on this graph, what's true about the temperature during that plateau? It's constant. Then after a small section of it being constant, right, the temperature increases until it reaches another plateau. Okay? We'll finish this. You know what? I'll finish reporting this discussion, and we can do it sometime. So we got to move on to the next thing. So okay. I have to.
So you're gonna keep talking after we leave?
Eventually, yes. Not right now.
And then